An oscilloscope is supposed to be our window into the soul of an electronic circuit, right? It's how we see what's really going on in there. But what happens when that window is dirty? What happens when you can't be sure if what you're seeing is the truth or just some funhouse mirror reflection?
So picture this. You've spent weeks, maybe months on a new design. You finally power it up, you hook up your probe, and you see the image on the left. It's this noisy, rounded, just awful looking mess. Your heart just sinks. Because what you expected to see, what you designed, is the beautiful, crisp signal on the right. Welcome to what I call the measurement mystery.
And that's the million-dollar question, isn't it? Did you just spend all that time designing a dud? Or is your most trusted piece of gear, your scope, actually lying to your face? Well, we're going to get to the bottom of it. All right, every good investigation starts with the primary suspect. And in this case, that's the oscilloscope itself. To figure out if it's lying, we've got to learn to speak its language. And that means decoding its most important specs. So the first thing everybody looks at is bandwidth. It's the big number they print on the front, right? It's what you pay all the money for. It tells you the maximum frequency the scope can supposedly measure. But, and this is a huge but, there's a catch. Check this out. See that point on the graph, the one labeled -3 dB? That is the scope's official rated bandwidth. But look at what's actually happening there. At that exact frequency, the signal you see on your screen is already down to just 70% of its real-world amplitude. Let that sink in for a second. That's a nearly 30% error. The scope is already lying to you, big time, right at the number it advertises on the box. And that's exactly why we have the 5 times rule. It's a super important rule of thumb. If you want an accurate measurement, let's say with less than 2% error, you need a scope with at least 5 times the bandwidth of the signal you're trying to measure. This is extra critical for digital signals because those sharp square edges are made up of much higher frequency harmonics. If your scope can't see those, your perfect square wave turns into a sad rounded blob. You're basically measuring a fantasy.
Okay, so you did the right thing, you bought a scope with plenty of bandwidth, you followed the 5 times rule, but your signal still looks terrible. What gives? Well, it's time to turn our investigation to a new suspect, one that's easy to overlook but is often the real killer.
This is so important. We all tend to think of the probe as just a piece of wire, right? A passive observer, just listening in. But that is completely wrong. The second you touch that probe to your circuit, it literally becomes part of your circuit. It's not just watching the show, it's on stage, changing the performance.
Now, this interference, which we call loading, comes in 2 main flavors. You've got resistive loading, which usually isn't a big deal thanks to the probe's high 10 megaohm resistance. But then there's the secret villain of our story, capacitive loading. This is the one that murders signal integrity, especially when you're dealing with anything fast. So what the heck is input capacitance? Just think of it like a tiny, invisible capacitor right at the tip of your probe. It's measured in these crazy small units called picofarads. But even though it's tiny, at high frequencies, it acts like a leak. It starts siphoning off the high-frequency energy from your signal, the very energy that makes up those sharp edges, and dumps it to ground. It rounds off your square waves and slows everything down, giving you a totally false picture of what your circuit is doing.
And here's the smoking gun. I mean, look at this. On the left, we've got a signal measured with a standard probe, about 9.5 picofarads. See that slow, rounded edge? That's a lie. Then on the right, it's the exact same signal point, but measured with a low capacitance probe. That's only 3.9 picofarads. Bam! The edge is sharp, it's fast, it's true. That's reality. The difference is just absolutely night and day.
So this is it. This is the big aha moment. When you're looking at probes, don't just get hypnotized by the bandwidth number. Look for the input capacitance. Find this number. Anything under 4 picofarads, like this 3.9 PF example, is going to show you what's actually happening. This is the spec that solves the mystery. Okay, we've unmasked our villains, not enough bandwidth, and too much probe capacitance. So now that we've solved the case, let's talk about what you can actually do about it. The practical, hands-on techniques to get a true signal every single time. All right, the single most important thing you can do right now is to shorten your ground loop. You know that long alligator clip that comes with every probe? Yeah, that thing. It's super convenient, but its length creates a big loop that's basically a perfect antenna for sucking in all the electronic noise floating around you.
Even worse, that length adds inductance, and that's what causes that nasty ringing you see on digital signals. Your goal should be to make the path from the probe tip to ground as short as physically possible. And this picture shows the ideal setup perfectly. Ditch that long ground lead. Use a little springy ground tip, or what's called the tip and barrel method. See how the ground connection is just millimeters away from the signal? That short, tight connection is your absolute best defense against a lying measurement. So, let's just quickly recap the best practices. Number 1, keep those ground leads short. Use the right accessories for the job. If you happen to be using a differential probe, just twisting the leads together works wonders for rejecting noise. And please, don't forget the 2 golden rules we uncovered. Follow the 5 times rule for bandwidths, and always check that probe capacitance number. We have covered a ton of ground here, so let's pull it all together into a simple way of thinking. A framework that'll help you pick the right scope and the right probe so you can finally measure with confidence. Think of this as your quick cheat sheet. If you're doing high-speed digital stuff, it's simple. You need tons of scope bandwidth and that magic low-input capacitance probe we've been talking about. But if you're trying to measure tiny ripple on a power supply, your priorities change. Now you care way more about the scope's vertical sensitivity, the millivolts per division. And you'll probably want a 1x probe because they generally have lower noise and let you see those really tiny details. It just goes to show, the right tool always depends on the job. So, we started with a mystery. This unsettling idea that your most important tool could be fooling you. But now, you know the secrets. You know how to see through the deception, how to choose the right tools, and how to use them to find the real truth in your circuit. You can actually trust what you see on that screen. So the only question left is, now, what are you going to go build?